As I mentioned in the previous lecture, we're going to barely touch the tip of the digital logic iceberg. But in today's lecture, I thought it might be interesting to look at some very fundamental but useful circuits, which are simple enough to understand, but require more than just one or two components in order to produce the output that's expected. If you take a look at a circuit like this one, this one is simple enough to figure out what it is that it does. Notice that what we have is essentially, we have inputs coming in from two different sources. We have an A0, A1, A2, and A3 coming into exclusive OR gates, and a B0, B1, B2, and B3. Now note that because all four of those digital logic components are exclusive OR gates, that they will produce a 1 only if the inputs are different from each other. So when we look at the output here with from the 4-input NOR gate, this would output a 1 if any of the bits coming in is equal to 1. Otherwise, it would produce a 0. So if all of the inputs are zeros, we'll get a result of 1. If any of the outputs is 1, we'll get a 0 because of the NOR gate. Well, what this is a 4-bit comparator. If the A0 bit is equal to the B0 bit, the exclusive OR gate will output a 0. If A1 is equal to B1, the second gate will output a 0, and so forth. If they differ in any of those bits, for example, if A2 is not equal to B2, then the exclusive OR gate will output a 1, and that would cause the NOR gate to output a 0. But if all of them are equal to each other, all of them will produce a 0, and then 4 zeros going into a NOR gate will produce a 1, and so this will check to see if the 4-bit number A is equal to the 4-bit number B. If they are equal, the circuit outputs a 1 for true. If they differ in any one or more bits, then the circuit will output a 0, which means false, that A is not equal to B. In order to implement addition, as for example in the arithmetic and logic unit, what we have to do is develop a circuit that will take the corresponding bits of two numbers, add those bits, and produce a sum bit and a carry bit. The carry bits then have to move over to the next digit in the result register, and so the addition is going to have to be able to handle 3 inputs and produce a sum bit and a carry bit. Now we'll look at some of the circuits that do this and build up to the idea of what's called a ripple carry adder that will allow us to construct up to any number of bits as an adder to take 2 input values, multi-bit values, and produce a sum of those 2 values that's consistent with the rules of arithmetic. Here's the idea of an addition circuit. We call this a half adder because it takes only 2 inputs, and then it produces a sum bit and a carry bit. Notice that what we've done here is we've created a circuit from a truth table that specifies exactly what we want to have happen for each possible pair of inputs. If A is equal to 0 and B is equal to 0, we want the sum to be 0 and the carry to be 0. If A is 0 and B is 1, or A is 1 and B is 0, we want the sum bit to be equal to 1 and the carry bit to be equal to 0. In the case that A and B are both equal to 1, we want the sum bit to be 0 and the carry bit to be 1. Now, you might note that the sum bit, as it's represented in the truth table, is the exact representation of the XOR operator, the Boolean XOR operator. That is, you get 1 only when the 2 inputs are different from each other. And the carry bit is exactly the Boolean AND operator. That is, we get 1 only when both of the inputs are equal to 1. Now we extend the half adder to be a full adder, which means that we have 3 inputs, that is, the bit from A and the corresponding bit from B, and a carry in that is provided by adding the lower order digits before we come into this. Now, some things to note about the truth table here. If you look at the sum column, we have a 3-input Boolean function that produces the sum bit for bitwise addition. Now, notice that the sum column is exactly the circuit that we implemented in the previous lecture. So the point of this is that we can tell the system what we want the output to be, and then we can write a Boolean function, or we can design a circuit, or we can design a truth table, and then we can produce exactly the output that we specify. So what's happened here is that we wanted to design an addition circuit. So we put down all the possible combinations of A and B and the carry bit, and we said, okay, in each of these cases, here's what we want the sum to be, here's what we want the carry to be, and then by taking the rows of the truth table that produce 1 for the sum bit, we can design that part of the circuit. And by taking the rows that give a 1 in the carry out bit, we can produce the carry out circuit. Now, if you split the circuit up a little bit, you can see where both of these circuits are developed, although these circuits were developed independently, that we can integrate them into one circuit, and then we can have in the top part of this diagram, we have A and B, and let the carry in be C. Then you have 2 exclusive OR gates to produce the sum bit, which is exactly what we did in the previous lecture. Similarly, you can produce the function for the carry out bit, and you do that in the same way that we produced the circuit for producing the sum bit from 3 inputs. Finally, we integrate multiple full adders into a circuit to create what's called a ripple carry adder. Note that each of the full adders would have that full adder circuit, and so as we wire this, we take the bit number 0 from X and bit number 0 from Y, and start out a carry bit of 0, and put those 3 inputs into a full adder. That would produce the sum bit for the bit number 0 in the result, and would also produce a carry bit that would ripple over to the next adder. That would have inputs of the number of bit number 1 from X, bit number 1 from Y, and carry bit number 1 from the previous full adder. And so that ripples across, all the way across this circuit, to produce the correct sum bits and the correct carry bits. And if there's a carry bit that goes out to carry bit number 4, then we have overflow. Now, of course, this is just a 4-bit ripple carry adder, but you should be able to at least imagine how this would be extended to be an 8-bit, a 16-bit, a 32-bit, a 64-bit, even 128-bit ripple carry adder could be designed once you have the full adder circuit. Now, this makes it look like it could be slow to do addition, but remember that electricity is traveling through this at the speed of light, and so when the arithmetic and logic unit is signaled to do this kind of addition, the entire circuit is set into a certain state instantaneously as the sum bits and carry bits are produced. They make it contribute to the next full adder in the ripple system. So if we think about this as rippling across, that's really thinking about it being too slow. The whole thing will happen instantaneously. Now, there are lots and lots of different kinds of circuits that we could look at. There are multiplexers, there are demultiplexers, there are shifters, there are complementers, and so on and so on. And engineers are working all the time to develop new and faster ways of doing various operations. So we've looked only at a very few circuits, but these are extremely useful circuits. Remember that we said that that all an arithmetic and logic unit needs is an addition circuit, which would be this ripple carry adder, a complementer, and a comparator. So we have essentially all the circuits you would need to design a computer, but of course these things are augmented by multiple other kinds of circuits that make things much faster and much more efficient.